Between 9 a.m. and 9:15 a.m. on Fridays, Sven's florist shop receives the X distribution of phone calls shown. So in this particular window on Friday, so between 9 a.m. and 9:15, Sven has some data about the number of times he got so many phone calls. So 12 times there were no phone calls at all. 18 times there was one phone call, and just one time there were 6 phone calls. What do we need to do? Find the mean of the X distribution, compare the actual data with that generated by a Poisson model. Now, a Poisson distribution it's to do with a mean. You have a parameter. We're going to use the letter M, and that's sort of the mean in a given window. So what we're going to do, once we find the mean, we're going to use that mean to generate expected frequencies using a Poisson model. So we can't really do that until we have the mean, but once we do, it'll be a lot easier. Find the standard deviation of the distribution. How close is it to the square root of the mean? So the square root of the mean would be the standard deviation of the Poisson equivalent distribution, and we'll find the actual standard distribution. To be fair, we're going to do A and C quite easily. I'm just going to use a calculator method. So if we just go onto the calculator statistics mode, if you've got old lists in there, we need to get rid. So we need 0, 1, 2, 3, 4, 5 and 6. We need the frequencies of 12, 18, 12, 6, 3, 0 and 1. And then we just can go to calc and settings. You need to make sure that your calculator knows that it's a frequency table. List 1, list 2, that means list 1 is the actual variable, which it is, and then this means that list 2 is the frequency of that variable, which it is. So that's right, that is a setup for a frequency table. So execute, then we go 1 var, there's only one variable, which is the number of phone calls. 1 var, and then we get this X bar, which is 1.5. So for part A, the mean X bar equals 1.5. Okay, so now for part B, what we're going to do, we're going to assume that this variable X is distributed according to a Poisson model, and Poisson only has one parameter, which is the mean and the variance, and we're just going to put it in as this 1.5. And remember, the Poisson model, it can generate expected probabilities which can easily be turned into expected frequencies. Remember, Poisson distribution applies when you have a fixed time window and you're looking for how many occurrences happen within a time window. There are other conditions as well to be met, but basically that's what we're looking at here. So P x equals x for a Poisson distribution. So P x equals x equals m. M is this 1.5 to the x e to the minus m over x factorial, and then x can be 0, 1, 2, 3, 5, 4, 5, 6, so on. It's only for discrete data sets. It certainly can't, and x couldn't be, say, 1.6. It can only be a whole number of things. So then what we are going to do, because I'm generating lots of things of repetitive nature, and because the x's go up in ones, I'm going to use table mode for this. So my function is going to be m is 1.5 to the x e to the minus 1.5 over x factorial. So if I just put that in, that should give me some Poisson probabilities. So I'll do that first, then we'll talk about how we're going to turn them into expected frequencies. So if we go to table mode, if you've got a function in there already, get rid. So it is 1.5 to the power x times e to the power of minus 1.5 all over x factorial. Factorial can be found in option and prob, and it's just there, x factorial. So that's the table. Then we need to set it up, and we want to go from x equals 0 to x equals 6. So from 0 to 6, and we want to go in steps of 1. Okay, let's have a look at the table now. These are probabilities, right? So I'm not going to write those down because we shouldn't need much of a tweak to turn these into frequencies. Okay, so they are probabilities, which are effectively, they could be thought of as relative frequencies. Now, what we need to do to scale those up into frequencies, if we look at the table, in fact, if I go back to my stats mode, and I go back to my calculations, calc 1 var, it tells me that n is 52. I could have added these up. So that n is 52 is the total frequency. Right? If I was to take this function and times it by 52, so the expected frequency is going to be, for a Poisson distribution, it's going to be, in this case, 52 times 1.5 to the power x times e to the minus 1.5 over x factorial. So if I just go back and change and put that 52 in, it should turn these into expected frequencies, which I can compare. I go back to table mode. Just going to go into the function, and I'm going to do 52 times. Go back to our table, and here we now have some frequencies that actually look quite similar. So now I'm going to write these down. So the first one, we have x and we have e to the x, or not e to the x, we have the expected value of it, so expected frequency. Expected number of times it would happen. So according to the Poisson distribution, we have 11.6. 11.6 times you would expect no cause if a Poisson model was a good fit. 17.4 for 1. For 2 we have 13.1. For 3 we have 6.53. For 4 we have 2.45. For 5 calls, 0.73. And for 6 calls, we have 0.18. So these are the expected frequencies if the distribution followed a Poisson distribution. So if these things were distributed according to a Poisson distribution. Right, so now we need to compare the actual data with that generated by a Poisson model. Well, if you look at it, it starts off really, really well. So 11.6 compared to 12, 17.4 compared to 18, 13 compared to 12 is not bad. 3 and 6.5, very, very close. 2.45 for 4, yeah, it's not too far. And then you can see here, in fact, I would say it's a very, very good fit. So I'm going to put very good fit. Okay, so find the standard deviation of the model. So that means the actual standard deviation using the frequency table, and we can go back to our statistics mode and just go to calc 1 var, and it tells me that sigma x is 1.29. So sigma equals 1.29. So that's from the actual data. And according to a Poisson distribution, the variance is 1.5, and the standard deviation would be the square root of 1.5. So the square root of 1.5 equals square root 1.5 equals 1.22, which again is pretty close. This is close. So overall, it looks like if Sven was interested, he could potentially apply a Poisson model to do his sort of predictions going forward. It may well be a very good solution to fit.